Right now, at this exact very moment in time, a spacecraft the size of a small car is drifting through the emptiness between the stars, and it has just detected something that should not exist at all. Right now, as of this year, 2026, Voyager 1 is approximately 25.4 billion kilometers from Earth, which works out to roughly 16 billion miles. To put that distance into perspective, the distance from Earth to the Sun is about 150 million kilometers. Voyager 1 is currently more than 160 times farther from the Sun than we are, and what it has just discovered out there, what its instruments have been quietly detecting for years now, is evidence of an invisible boundary in space that separates two completely different regions of the universe. Scientists still cannot fully explain what that boundary actually is. Subscribe now before we go any further into this story, because what NASA has confirmed about this invisible wall that Voyager 1 has crossed is one of the strangest, most quietly remarkable scientific findings in the entire history of interstellar space exploration. Let's start with where Voyager 1 actually is, because most people have absolutely no idea how far this machine has traveled. Voyager 1 launched on September 5th, 1977 from Cape Canaveral in Florida. That was nearly half a century ago. Its original mission was straightforward enough. Fly past Jupiter, fly past Saturn, collect data, and send it home. Nobody at NASA seriously expected the spacecraft to still be operating in 2026. Nobody expected it to still be transmitting anything at all. But right now, the signal it sends home, traveling at the speed of light, the fastest anything in the universe can possibly travel, takes more than 23 hours just to reach us. And NASA has confirmed that by November 18th, 2026, that signal travel time will hit exactly 24 hours, making Voyager 1 the first human-made object in history to sit one full light day from Earth. The project manager at NASA's Jet Propulsion Laboratory, Susie Dodd, explained it simply. If you send Voyager a good morning message at 8 in the morning on Monday, you will receive its response at 8 in the morning on Wednesday. That is not a metaphor. That is the actual operational reality of managing a spacecraft in interstellar space right now in 2026. Now here is what makes all of this even stranger. Voyager 1 is not just far away. It is in a completely different region of the universe from anything humanity had ever directly sampled before. In August 2012, Voyager 1 crossed a boundary called the heliopause, the outermost edge of the heliosphere, the enormous bubble of solar wind and magnetic influence that our sun produces and that surrounds our entire solar system, extending well beyond the orbit of Pluto. When Voyager 1 crossed that boundary, it became the first spacecraft in human history to leave the heliosphere and enter what scientists call the very local interstellar medium, the actual space between stars, not the edge of it, not the outer boundary of the solar system, but interstellar space itself, the realm of the stars, where the sun's influence gives way entirely to the wider fabric of our galaxy. And out there, in that almost unimaginably empty region of space, something unexpected began to happen. Voyager 1 picked up signals. Not radio signals in any traditional sense. These were plasma waves, ripples and vibrations moving through the thin ionized gas that permeates even the emptiness of interstellar space. The spacecraft's plasma wave system, an instrument built with two antenna rods stretching about 10 meters behind the spacecraft, was designed to detect exactly these kinds of oscillations. When converted into audio signals by scientists, these plasma waves produce actual sounds that you can hear. For years, after Voyager 1 crossed into interstellar space, the plasma wave system would occasionally detect bursts of plasma oscillation, sharp momentary signals triggered when enormous shock waves produced by the sun, ejections of solar material blasted outward from the sun's surface, traveled all the way to the heliopause and sent ripples reverberating out through the interstellar medium. These were brief, dramatic moments, like hearing a clap of thunder in an otherwise quiet sky. They gave scientists precise snapshots of the electron density in the interstellar medium at specific moments. But because those shockwave-triggered events were rare, occurring roughly once a year at most, the picture of what interstellar space actually looked and sounded like between those events remained frustratingly sparse. Then, in research published in May 2021 in the journal Nature Astronomy, a team of scientists led by Stella Coer, a doctoral student in astronomy at Cornell University, alongside professors James Cordes and Shami Chatterjee at Cornell, and working with instrument experts Donald Gurnett and William Kurth at the University of Iowa, reported something remarkable. Going back through Voyager 1 data stretching from 2017 onward, they had identified a completely different kind of signal, a faint, persistent narrowband hum that never went away. Not a momentary burst triggered by a solar shockwave, a constant, continuous, barely detectable emission from the interstellar plasma itself, present all the time in the quiet between storms. Coer described it as very faint and monotone, sitting in a narrow frequency bandwidth, like the difference between a lightning bolt and a gentle, persistent rain. James Cordes, her professor at Cornell, compared it to exactly that. In the case of a solar outburst, He said it is like detecting a lightning burst in a thunderstorm, and then it is back to a gentle rain. That gentle constant rain is what Voyager 1 has been detecting continuously in the years since. This matters for reasons that go well beyond the novelty of a spacecraft detecting something strange. Measuring the electron density of this interstellar plasma precisely and continuously, indicated by the pitch of the hum Voyager detects, tells astronomers about the structure of the interstellar medium in ways that simply could not have been measured by any telescope on Earth. And this steady measurement has already revealed something deeply interesting. The interstellar medium is not uniform. It is not a smooth, featureless emptiness that Voyager 1 is drifting through. It has density fluctuations, patches of slightly denser or slightly thinner plasma, on scales of about 1 astronomical unit, meaning roughly the distance from Earth to the Sun, spread across the 10 astronomical units of interstellar space that Voyager 1 has been sampling since 2017. These density fluctuations are evidence of interstellar turbulence. The same kind of large-scale chaotic motion that exists in the ocean or in Earth's own atmosphere, but stretched across distances that dwarf our entire solar system. But here is where the story takes a genuinely strange turn. In 2020, Voyager 1's magnetometer registered a sudden, abrupt jump in the intensity of the magnetic fields embedded in the interstellar plasma it was passing through. At the same time, its plasma detector measured a corresponding rise in plasma density. Scientists had seen brief, transient jumps like this before, caused by solar shock waves rippling outward from the Sun and compressing the interstellar medium as they passed through it. These shockwave events are dramatic but temporary. The Sun constantly ejects material into space through solar wind, a continuous stream of charged particles flowing outward from the Sun's corona. Occasionally, the Sun produces coronal mass ejections, enormous bursts of solar material that propagate outward at incredible speeds. When these waves reach the boundary of the heliosphere and compress the interstellar medium beyond it, they create temporary density increases and magnetic field fluctuations. Those previous jumps had always returned to baseline levels after a few months. The pattern was clear and predictable. But the 2020 anomaly was different. It did not return to baseline. The elevated magnetic field intensity and plasma density persisted, stubbornly holding at the new, higher level month after month, far beyond what any previous solar shock wave event could explain. This was not a temporary compression. This was something else entirely. Adam Szabo, an astrophysicist at NASA's Goddard Space Flight Center and the principal investigator for Voyager 1's magnetometer, offered one genuinely remarkable possible explanation. He suggested that Voyager 1 may have entered a small ancient cloud of interstellar plasma, a cloud carrying a higher magnetic field than the surrounding interstellar medium, because it was originally produced by a completely different star or star-forming region long ago. This is not an abstract speculation. Interstellar space is not a uniform void. It is a landscape of distinct regions, each with its own history. Some clouds were created by nearby stars millions of years ago. Others were produced by massive stellar explosions, supernovae that blasted material outward and left it floating in the dark between the stars. Each of these clouds retains the signature of its origin written into its magnetic fields, its particle density, its chemical composition. When Voyager 1 entered one of these ancient clouds, the instruments detected a change. The magnetic field grew stronger. The plasma density increased. The hum detected by the plasma wave system shifted subtly. In other words, Voyager 1. We 1 may have drifted from one distinct pocket of interstellar material into another, each with its own measurable distinct properties left over from entirely different cosmic origins, essentially crossing an invisible boundary in deep space between the remains of our own sun's influence and the ancient remnants of some other star's history. Think about what that means. Voyager 1 is carrying our fingerprints across the boundary between our star system's domain and the domain of another star entirely. It is the first human creation to ever enter the shadow of another sun's ancient influence. Scientists cannot confirm this theory without more data, which is precisely why every piece of information Voyager 1 sends home is so extraordinarily valuable, and which is why the 2023 communications blackout was so frustrating. In November 2023, a corrupted chip in one of Voyager 1's flight data system computers caused the spacecraft's transmissions back to Earth to become completely unintelligible, essentially turning its data feed into garbled nonsense. For 6 months, one of the most scientifically productive spacecraft ever built was effectively unable to communicate. Engineers at NASA's Jet Propulsion Laboratory worked through the problem from over 20 billion kilometers away, carefully diagnosing the issue and devising creative solutions to work around the damaged chip entirely. They essentially rewrote the software that controls the spacecraft's communication systems remotely, with every command taking more than 22 hours to arrive and every response taking another 22 hours to come back. By May 2024, they had restored Voyager 1's ability to send back usable scientific data in what was widely described as one of the most remarkable remote engineering feats in the history of space exploration. But restoring communications was only half the battle. Voyager 1 faces a challenge it cannot be fixed out of. The spacecraft runs on 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 into electricity. These generators have been slowly losing power since 1977 at a rate of roughly 4 watts per year. By April 2026, they were producing less than half of their original electrical output. That steady power decline forces NASA engineers into an extremely delicate ongoing balancing act. Every watt of power saved by turning off one system is a watt available to keep something else running. If the power levels drop unexpectedly and trigger the spacecraft's automatic undervoltage fault protection system, that system will shut down components on its own to protect the spacecraft. And recovering from that unplanned shutdown could take weeks of careful, slow remote work. That is exactly what nearly happened in February 2026. During a routine roll maneuver on February 27th, Voyager 1's power levels dropped unexpectedly, bringing the spacecraft dangerously close to triggering that automatic fault protection. To stay ahead of the threshold and give engineers room to breathe, NASA made the decision to manually shut down one of Voyager 1's remaining science instruments, the Low Energy Charged Particles Experiment, known as the LECP. On April 17, 2026, the LECP had been operating almost continuously since Voyager 1 launched in 1977. 49 years of nearly uninterrupted operation, measuring ions, electrons, and cosmic rays in the interstellar medium and providing critical data about the structure and pressure of the space beyond the heliosphere. Turning it off was not a decision made lightly or casually by the engineering team. Engineers left only a tiny motor component inside the LECP running, consuming just half a watt of power, specifically to preserve the possibility of restarting the instrument in the future if enough power can be freed up. Shutting down the LECP is expected to give Voyager 1 approximately 1 additional year of operational breathing room. During that window, NASA engineers are preparing what they have internally nicknamed the Big Bang, a high-stakes power management upgrade designed to replace several older power-hungry components on the spacecraft with lower power alternatives, all in one coordinated operation. The name reflects just how significant and risky this procedure is. The team planned to test the Big Bang first on Voyager 2, which has slightly more power to spare and is closer to Earth, making it a safer test subject for the procedure, with tests scheduled for May and June 2026. If those tests go well, the same upgrade will be attempted on Voyager 1 no earlier than July 2026. If the Big Bang succeeds, it could keep both Voyager spacecraft operational with at least one functioning science instrument each well into the 2030s. It might even free up enough power to restart the LECP on Voyager 1. If it fails, the consequences could be severe and potentially irreversible. What 2 science instruments remain active on Voyager 1 right now are the plasma wave system, the very instrument responsible for detecting the hum we started with, and the magnetometer, which measures the magnetic fields embedded in the interstellar plasma. Together, these 2 instruments are quietly continuing to do something no other human-made object has ever done, directly measuring the properties of the interstellar medium in real time from inside it. Every piece of data Voyager 1 sends back is a direct, first-hand measurement from a place no spacecraft has ever reached before. There is no other source for this information. No telescope on Earth or in orbit can substitute for it. It can only come from a 49-year-old machine drifting alone through interstellar space, still humming along, still listening to the sounds of the galaxy around it. The only reason NASA can still send commands to Voyager 1 and receive its data is because of the Deep Space Network, a global system of enormous radio antennas located in Goldstone, California, in Madrid, Spain, and in Canberra, Australia. These 3 sites are deliberately spaced around the world so that, as Earth rotates, at least one of them is always pointed in the right direction to communicate with deep space missions. This redundancy is absolutely essential. If a single antenna went down, communication with Voyager 1 could be lost for hours at a time, and with the signal taking 23 hours to cross the Gulf of Space, maintaining continuous contact requires constant availability. The largest antennas in the network are 70 meters wide, roughly as tall as a 20-story building, and they are some of the most precise radio receivers ever built. These antennas have been specifically designed and maintained to detect signals so faint that they are barely distinguishable from background noise. Even with those enormous dishes, the signal arriving from Voyager 1 is so incredibly faint by the time it crosses 25 billion kilometers of space that it carries only about 160 bits of data per second at most. To put that in context, a standard home internet connection transmits data millions of times faster. A high-definition video stream requires millions of bits per second. Voyager 1's data rate is slower than a telegraph transmission from the early 20th century, and yet that faint whisper of data is packed with scientific information that no other instrument can provide. Everything Voyager 1 has ever told us about interstellar space has arrived at that trickle of a data rate painstakingly accumulated over months and years of continuous listening. The entire computing system on Voyager 1 has roughly 70 kilobytes of memory. A single low-resolution photograph on a modern smartphone takes up more space than the entire memory capacity of humanity's most distant spacecraft. Its main transmitter generates about 22 watts of power, roughly the same as a refrigerator light bulb or a small camping lantern. That 22-watt signal, by the time it crosses 25 billion kilometers of space and arrives at the enormous dish antennas of NASA's Deep Space Network on Earth, has lost virtually all of its energy. The received signal is billions of times weaker than it started. NASA's enormous ground antennas have to strain to detect it at all. And yet that faint, barely there, whisper of a signal produced by a refrigerator bulb transmitter on a craft built in a decade when handheld calculators were considered cutting edge carries real scientific data about the interstellar medium that no other instrument anywhere can provide. Voyager 1 originally launched with 10 science instruments. As the decades have passed and power has declined, those instruments have been switched off one by one. Each retirement a small scientific loss traded for the survival of what remains. The imaging cameras went dark in 1990. The ultraviolet spectrometer followed. The cosmic ray subsystem was powered down in February 2025. One by one, the eyes and ears of Voyager 1 have been closed. What remains now are only two instruments, the plasma wave system and the magnetometer. These are the last two direct first-hand sensors humanity has in interstellar space. When they finally go dark, nothing will replace them because no successor interstellar mission has been approved, funded, or built. The earliest any new interstellar probe could realistically be launched and reach Voyager 1's current position would be decades from now, long after the scientific window on whatever Voyager 1 is currently measuring has permanently closed. The invisible boundary that Voyager 1 detected in 2020 still has no fully confirmed explanation. The plasma cloud anomaly persists. The magnetic field intensity and density remain elevated. Scientists have a theory. They believe that Voyager 1 may have entered a pocket of ancient interstellar material created billions of years ago by some other star, or perhaps by a stellar nursery that no longer exists, perhaps by a massive star that exploded in a supernova before Earth even formed. The evidence for this is indirect but compelling. The magnetic field strength and plasma density did not return to baseline. They hold steady at the new higher level. This is not the kind of temporary fluctuation that solar shock waves produce. Solar shock waves are violent but brief. They expand outward, compress the medium in their wake, and then disperse. The effect they create is transient, a momentary spike that fades as the energy dissipates. But what Voyager 1 detected does not fade. Month after month, the readings remain elevated. Year after year, the signal persists. This is a boundary. This is a wall. This is Voyager 1 passing from one region of the interstellar medium into another, each with its own distinct properties, each with its own history written into its magnetic fields and particle density. The magnetic fields tell a story. They reveal how charged particles have been compressed and organized by forces we can barely imagine. The plasma density tells a story. It reveals how much material is in this region compared to the surrounding space. Together, these measurements paint a picture of an environment shaped by cosmic forces acting on timescales of millions or billions of years. Voyager 1 crossed that invisible boundary years ago, and it is still in the region beyond it right now, still transmitting data about what is on this side of the wall, still providing humanity with its first continuous real-time map of the very local interstellar medium, still doing something no other spacecraft anywhere can do, still measuring a frontier that no human being will ever visit in person, still serving as our eyes and ears at the edge of our galaxy's local neighborhood. The signal from a Voyager 1 carrying all of this data will arrive at Earth on November 15th, 2026, taking exactly 24 hours to complete its journey. That same day marks another milestone. Voyager 1 will sit exactly one full light day from the planet that built and launched it, farther from home than any human-made object has ever been. The spacecraft that was designed for a 4-year mission, built with the computational power of a basic pocket calculator, powered by nuclear generators now more than 4 decades old, communicating across a gap so enormous that a simple command and response exchange takes 2 full days to complete, will reach a new remarkable record that defines the outer limits of human technological achievement. It will be the most distant human-made object ever to transmit data home, and it will still be listening. It will still be detecting the faint hum of the interstellar plasma. It will still be measuring the magnetic fields of this ancient cloud region. It will still be sending home the crucial data that humanity needs to understand what lies beyond the heliosphere and what profound mysteries wait in the vast spaces between the stars throughout our galaxy. The The Big Bang power upgrade scheduled for July 2026 represents one final crucial attempt to keep Voyager 1 operational and functioning into the 2030s and beyond. If it succeeds, the spacecraft could continue its observations for years to come. If it fails, the mission may end in weeks or months, but either way, what Voyager 1 has already accomplished is nothing short of extraordinary. It has traveled farther than any machine humanity has ever built. It has entered a region of space no instrument has ever reached. It has detected signals that told us the interstellar medium is not uniform, that it has structure and texture and history. It has found evidence of an invisible boundary between regions of space with different properties, each carrying the signature of different cosmic origins. And it did all of this while operating on power levels that would barely light a refrigerator bulb, while transmitting data at rates slower than the earliest days of the internet, while engineers back on Earth worked miracles to keep it alive. Rerouting power, rewriting software, performing surgery on a spacecraft from a distance of 25 billion kilometers. Consider the full arc of this mission for a moment. In 1977, a group of engineers built a spacecraft with the computational power of a basic pocket calculator, loaded it with scientific instruments, pointed it at Jupiter, and launched it into the sky. They hoped it would last 4 years. It has now been operating for 49 years. It has flown past Jupiter, past Saturn, past the outer reaches of the solar system, through the heliopause, and into interstellar space. And it is still going, still transmitting, still detecting the faint electromagnetic hum of a galaxy that existed for billions of years before the first human being ever looked up at the night sky and wondered what was out there. The engineers who built Voyager 1 had no idea that their machine would carry humanity's message so far. They had no concept of what they were really creating. They were building something that would outlive almost everyone who worked on it. Something that would continue its mission for decades longer than anyone predicted. Something that would eventually venture into a region of space no instrument from Earth had ever reached and find mysteries waiting there. If there is one thing this entire story demonstrates, it is that the universe does not yield its secrets easily or quickly. The invisible boundary that Voyager 1 discovered was not a sudden dramatic announcement. It was an anomaly that scientists had to work years to understand. The ancient plasma cloud theory still awaits full confirmation. The Big Bang power upgrade has not yet been proven to work. Every answer Voyager 1 has given us has arrived slowly, quietly, across a gap of billions of kilometers and a trickle of data barely faster than the earliest days of the internet. And yet every single piece of that data is irreplaceable. There is nowhere else in the universe that humanity can currently go to get it. Telescopes can only observe from a distance. Voyager 1 is there, on the scene, taking measurements directly. In a way, Voyager 1 is not just exploring the cosmos, it is bringing the cosmos home to us. If you want to keep following this story as the Big Bang procedure unfolds on Voyager 2 this summer, as the same upgrade is eventually attempted on Voyager 1, as that one light day milestone arrives in November 2026, and as whatever data comes next slowly makes its 23-hour journey home to Earth, hit subscribe now because there's genuinely no other mission in the history of a human spaceflight quite like this one. And no story in space science right now that is more quietly, persistently remarkable. Drop a comment and tell me what surprised you most. The fact that this spacecraft is still working and transmitting after 49 full years in space. The fact that a signal now takes more than 23 hours just to arrive from it. The fact that an invisible boundary in the interstellar medium was discovered by the fading hum of plasma waves. The fact that scientists are carefully managing every watt of power, turning off instruments one by one, fighting a desperate battle against the relentless decline of aging nuclear generators. The fact that an invisible wall separates our sun's ancient influence from the influence of some other star whose light we have never seen. Or the sheer scale of what Voyager 1 has accomplished, drifting one light day from home, still listening, still measuring, still sending home data that no other instrument anywhere can provide. This is what real space exploration looks like. Not sudden dramatic revelations, but patient, persistent observation. Not dramatic discoveries announced in press conferences, but slow, careful accumulation of data across years and decades. This is humanity reaching out beyond the solar system, touching the interstellar medium with instruments we built half a century ago. Still learning, still discovering, still wondering what secrets the galaxy holds. And for as long as Voyager 1 can still transmit, as long as engineers can keep it alive with their careful power management, as long as the Deep Space Network continues to listen, that journey continues. Thanks for staying all the way to the very end.